Hi, my name is Feline Hermans. I'm on Twitter as well. This is my handle. If you're tweeting about this, then do mention me so I can see what everyone is tweeting. I'm assistant professor at Delft University of Technology, and I'm here today to talk about spreadsheets. As you can see, spreadsheets are code. And this is not just the title of my talk. This is the gospel of my life. Spreadsheets are code. I literally go everywhere, all around the world, to tell people the happy word about spreadsheets. So you might not believe me, that's okay. I have 3 reasons for you why you should actually consider spreadsheets as pieces of source code. First of all, spreadsheets are used for very, very similar purposes. So what you see here is an investment calculation, you put in some numbers, and you get a result. And there's not really something spreadsheet specific about this problem. You could do this in Java, or in Objective-C, or in a spreadsheet. So I go to great lengths to make my point. To such great lengths, in fact, that I have implemented a Turing machine using just spreadsheet formulas. So you see it here, every row is an iteration of the tape, and with conditional formatting, I'm moving the head over the tape. So in addition to being proof that spreadsheets are Turing complete, I also think it's a pretty nice visualization of a Turing machine because you see what is happening. So that's the second reason that you should consider spreadsheets as source code. And many people on the internet really enjoy that. Cory Doctorow wrote a blog post about it, and it even brought my website down for a little bit because so many people were trying to download my Turing machine. So thirdly, spreadsheets suffer from lots of different problems, but all those problems are really software engineering problems. For example, only 1 in 3 spreadsheets have a manual. Spreadsheets stay alive for an average of 5 years, during which they're used by, for an average of 5 years, during which they're used by 12 different people. So these are like software engineering problems. If you define end users as people without an education in programming, in the 60s and the 70s, everyone was an end user programmer. There was no education, and everyone was just making the code that they needed for their jobs. And then of course, after a while, 10, 20 years later, many of those programs were still running, but there was no documentation, they had to be maintained by many different people, so that made modifying the problems hard. Typical software engineering problems that we know how to deal with. So in summary, spreadsheets are code because the activities, the complexity, and the problems around them are very, very similar. So that leads to the question that if spreadsheets are code, could we maybe use methods and techniques from software engineering to improve spreadsheets? Quick summary of my dissertation: yes, we can. It's very, very possible to take methods and techniques from software engineering and to use them within spreadsheets. And in the remainder of my talk, I'll give you a number of examples of how we did that. So if you look at software engineering, if you look at IDEs, modern IDEs have lots of tools that help you write good code. You can do debugging and testing and analyzing, and those features are really to help you be a responsible developer. They're not helping you write more lines of code, they're helping you write good code. So then if you look at Excel, well, it has none of those things. It doesn't have debugging and testing features. So here's me as a young PhD student, so young. I thought, those guys need an IDE. Spreadsheets, what they are lacking is a good development environment. So let's bring a few of those features that we in software engineering know and love, bring them to spreadsheets. So the first thing I did was a tool that extracts an architecture from spreadsheets to say. So the blocks here represent worksheets, and the arrows between them represent formulas going from the one worksheet to the other. So in this example on calculation 2, there are formulas using data from the input worksheet. So we visualized lots of spreadsheets that way, and we showed it to users, and there was lots of variety in the diagrams that we got. Some looked like this, pretty structured. Some look like this, pretty spaghetti. So what you see here, if you inspect the diagram a little bit more, that this is Q3, Q4, and Q2 with the months within them, but this is Q1 with January and February and March. So immediately looking at the diagram, you see that something strange is happening here. And the person that built this spreadsheet, of course, we asked him, why do you make it like this? What is different about Q1? He said, oh yes, now I remember. I started in Q1 making this model, but I didn't really know what to do yet. So then in Q2, I started afresh, building the model how it needs to be. And then I copied that in 3 and 4. But of course, as time goes, it became Q1 again, and he totally forgot the fact that Q1 was just a draft, and he entered the data then. So the visualization tooling immediately shows you those type of strange patterns. Other visualizations look like this. Different, but also a bit, not what you want. So this is sheet 1 and sheet 2 in Dutch, and this is one big fat arrow going between those two worksheets. So all the data is crunched, and there's lots of connections. And other worksheets look like this. This is not even one file. All those pink blocks represent external worksheets. So this spreadsheet takes data from lots of different data sources and combines it into one overview. This was an overview of many different branches and departments of this company, and they called this thing the mother sheet. So what we found, looking at all those different visualizations and having people look at all those different visualizations, is that users started to use the visualizations as means of diagnostics. So they looked at a visualization of a spreadsheet and they said, this visualization looks like spaghetti. That means the spreadsheet must also be structured not so good. And this idea led us to the path of code smells. Code smells for spreadsheets. Because if you think about it, spreadsheets are, I said it before, very similar to source code. If you think of a class as a worksheet and a formula as a method within a worksheet, it's very easy to transform known code smells from Martin Fowler to spreadsheets. For example, this formula, the sum of this block and that block and that block and that block, not really easy to read. You could say this has the too many parameter smells. There are too many things that you put into this formula. And another example here, an if, nested in an if, you could say that's the conditional complexity smell because you're nesting conditionals. So these are smells that occur at the formula level. So you look at one formula. But what we found is that smells can also occur at a more structural level. This is also what we saw a little bit in the visualizations. So for example, if we look at this smell, does anyone know what this smell is? What the name of this smell is? I did this talk at another conference and then someone in the audience yelled, bad naming, which is also true, but that's not the smell I was going for. This is the feature envy smell. So that method here is jealous of those nice little fields that class A has. He would actually rather be in that class. So it's pretty easy to see how that could apply to a spreadsheet. If you just replace class by worksheet and method by formula, you have the same thing. Let's look at an example of that. Here we are in the income statement worksheet, and we have a formula there that's only referring to cells in a different worksheet, in a required funds worksheet. So you can see how this is very tiring and annoying if you would have to debug this formula. You'd have to go, okay, what does it say? Required funds B9. What is that? Oh, that's buildings, amount of buildings. And then divided by required funds, C9, what is that? That is depreciation of buildings. Okay, the amount of buildings divided by the depreciation. And then we have to repeat that a number of steps. So you see that's really very tiring. And I didn't put people into MRI scanners like one of the future speakers will do, but you can imagine that it's very tiring for your brain to continue to switch between worksheets. And we're actually at this point running an experiment to measure how much harder you make it for users by organizing your spreadsheet like this. So the next step, of course, if you say smells, then you say refactoring. Yes, very good. If you have a smelly artifact, a smelly piece of source code, or a smelly spreadsheet, you want to refactor it. So what we did is we built a tool called Bumblebee that helps people refactor their spreadsheets. You can select a formula like this, this formula in your worksheet that might not be optimally structured. So here we have a smell divided by a count. That's not really nice. It would be easier if you would use an average there, and Bumblebee can detect it. So you can ask it, can you find applicable rewrites for me? And it will tell you, yes, you can do the sum and count to average refactoring, and you even get a little preview of how the formula will look like. Just as many IDEs also give you a preview of how a refactoring will look like on your source code. And if you like it, you can say, yes, I like that refactoring, let me apply it, and then automatically your refactoring is applied. And here we do it for one formula, but you can also do it for an entire worksheet or even for an entire workbook. If you want to get rid of a specifically smelly feature in a whole spreadsheet, you can do that too. So the next step in our research obviously was, if you say refactoring, you say testing. Very good, sir. If you're going to refactor a spreadsheet, you'd like to have some tests because you want to make sure that everything is correct. And this is historically the order in which we did the research. But it would be nicer to do tests before refactoring, because then you already have the tests. And I was thinking this will be so hard. It will be so hard to get spreadsheet users to test, because it's already so hard to get professional developers to test, to make sure they have time devoted to testing, not just because of them, but also because of management within companies. So how am I going to get spreadsheet developers to test their stuff? So that was typical ivory tower thinking, because I was thinking about how hard it should be instead of actually looking at what people do. Because if you inspect spreadsheets, you'll see that many of them have formulas like these. So if the sum of these cells is not 100%, then error, else 100%. This is like a test, right? This is like expressing those cells together should always be 100%. It's like the maker of this spreadsheet is communicating with me, the user, through a formula. So we thought, that's nice. Is this common? Yes, it's very common. We found that in 8% of spreadsheets, these type of formulas are already present. So we thought we could use that. We could extract those formulas from the spreadsheet and put them into something like a test suite. So we built another plugin called Expector. And with Expector, you can detect these type of formulas. So you can click here, find existing tests, and it gives you an overview. In this case, it's only one, but it can be many. We say, hey, that cell there on questionnaire B10, it expresses that the sum of that block should be 100%. So you see, we've manipulated the formula a little bit. We parse the formula, we have some heuristics, knowing what is good. We look at words like okay, good, yes. And this way we can detect what is the passing and the failing branch of the test. So you get a description in something like natural language. And if you say, yes, I would like to save that test, we save the test. We have now a test suite and we can run the test. So we can say, yes, all your tests passed and none of them have failed. And what you can also do, of course, if you have a test suite, is calculate coverage. So with Expector, you can ask, show me what is tested. We don't call it coverage, we just tell them this is tested. If you click it, you get a visualization, not just of the test cell, but because the test cell depends on the cells above it, we say, okay, we call them tested as well. Because if one of the 20s changes into something else, then the test formula will let the user know that. So we're not really talking sophisticated types of coverage here, like statement coverage or branch coverage. We're just giving the user an idea of what is tested, and in a similar way the user can also ask what is not tested, and then we visualize all the cells that are not yet covered by a test. So that was more or less the past of my research, everything that I have been doing up to this point. But of course this symposium is called the future, so what is next? So far we've more or less only looked at this direction, from source code to spreadsheets. Wouldn't it be nice if we could also go the other way around, from spreadsheets to programming, to source code? Because so far I've only said spreadsheets are code, which is true, but they're even more. Spreadsheets are not just a programming language, they are the best programming language that has ever existed in the history of mankind. I'm serious. Everyone can do spreadsheets. Everyone knows how to build a spreadsheet, except maybe for software developers. You know, your neighbor does his taxes in a spreadsheet, the soccer coach of your children is organizing the planning of the matches in a spreadsheet. Everyone knows this. There are only 11 million professional developers, according to InfoQ. But if you compare that to spreadsheets, there are 650 million Excel users. And of course, not all of them can program, but many of them can. There was a research by the Dutch Statistics Bureau that interviewed citizens of the Netherlands, and over 50% of citizens can use formulas in a spreadsheet. So if it's half of that 65 million, you know, even if it would be a third or a quarter, it still greatly outnumbers professional developers. So somehow spreadsheets have something that make it very easy for people to use them. So I think we as a software engineering community, we have to learn from that. We have to look at spreadsheets as a programming language, as a very good programming language, and think, what do they have to make it so easy for users? Resistance of spreadsheets is futile. So one of the things that spreadsheets have is a property called directness. And directness is the feeling that you are directly manipulating an object. And that sounds a bit vague, so let's look at an example in a spreadsheet. So here I have a bunch of people, a bunch of names, and I noticed I've made a typo in one. Because spreadsheets are so direct, I can just go to the cell and change the name. I point at what I want to change, and then it changes. And if I want to do something with my data, for example, I want to have a full name method, a full name formula, I just go to the cell where I would like to have that formula, and I type it, A2 and B2, and I concatenate them with a space in the middle. And if I want to do that for all my people, I just drag it down. This seems like a very, very simple idea, but if you look at how to do this in a programming language, you will see how not direct programming languages are. This is how a little bit of C# looks like, doing the same thing. So I need a person class that has fields, and I need a constructor before I can even do anything. Then I have to make instances of persons, of people, of that person type. And if I want to iterate over the people in my list, I have to put them in a list, like this. So lots of scaffolding needed before I can even do something with the people in my list. And then suppose I'm going the same way as I did in the spreadsheet, so I want to print everything, everyone. I have a loop, and then I do console.writeLine, person dot, crap. There is no full name method. I'm realizing that there's no full name method where I'm working with the types. So then I think, okay, I need a full name method. Where should that go? Okay, a person is in the collection of people. Okay, a people is a list of person. What is a person? Oh, I have to go to the definition of person, and then there is where I would add my methods. You see how many steps are needed to get to the point where I actually can change something. Programming, normal programming, makes it very hard for people to get stuff done. And the distance between where I'm working with my data and where am I defining objects and methods on that data, that distance can be really large. Here it is just within one file, but it can be in a different file as well. It can be in a different project, in a different library, it can be an API call. So it's very hard to see what to do. And I don't know, I don't have a solution for this, so if anyone wants to work on this, here's a free research idea. But somehow it would be interesting to try to make that distance smaller. Maybe I want to define a method here. Maybe I should just be allowed to define a method on an instance, and then later on we will figure out where that goes. I don't know how that will look like, but this is something I think we could work on. So a second amazing property that spreadsheets have is they are live. Does anyone know who made this visual? From what talk this is? It's from a talk by Brad Victor called Inventing on Principle, and it's a really amazing talk. You should definitely check it out. And the idea that he proposes is called live programming. He didn't invent it, but his videos certainly made it really famous recently. So the idea is, here you have code on the right-hand side, and on the left-hand side you have the instantiation of that code, which is a tree in this example. And if you change something to the code, let's say you make the leaves blue, it immediately updates. You don't have to do anything. You don't have to compile your code. You just change it and it updates. So spreadsheets have that live programming concept as well. If you look at a spreadsheet, here I have some data and a minimum. If I change a value, let's say I want to change that 8 into a 2, immediately the result is updated from the formula. I don't have to hit compile. I don't have to run anything. I just change the value and everything changes. So that liveness, wouldn't it be nice if we would also have that liveness within the IDE? If you didn't have to change anything, you didn't have to run anything to get a result of your code. So today here I'm demonstrating for the first time ever a new research idea that I've been working on together with Thijs van de Storm at CWI. We were trying to bring a little bit of that liveness of spreadsheets to programming. So let me show you how that looks like. So here we have data like in a spreadsheet, and we have a minimum column that calculates live. So I'm updating here, I make that plus into a times or into a divides, and it immediately updates without me doing anything. So what I can do now is I can actually implement a real minimum function. So here's a for loop that I was too lazy to type. And then I say, okay, if the argument I'm currently inspecting in this run of the for loop, if it's bigger than the minimum, then the minimum will take that value. And then you think, shit, nothing is updated. I must have made a mistake. So you go back to the code and you noticed, of course, you should have used a smaller n, and then you get the update. So this is not, of course, in the IDE yet, but that's where we want to bring it, where you have a visual representation of whatever you're building and the code right next to it, and without compiling, without running, just immediately, only by changing the code, your values will update. And we think that if we make that cognitive distance between the code and what it's doing smaller, it will make programming easier and enable more people to program. So that's everything I wanted to share with you today. But before I'm going to go over to the Q&A session, let me summarize my entire talk in 1 minute. So if you came in late or if you were a bit jet lagged, this is your second chance to get the gist of the presentation. First and foremost, spreadsheets are code. Don't forget it, tell all your friends, and don't send me mean reviews saying that spreadsheets are not code. Spreadsheets are code because they're used for very similar purposes, they are Turing complete, and they suffer from typical software engineering problems. So what I did in the early stages of my research is I used the inspiration from software engineering to make spreadsheets better. For example, by a tool that extracts architecture from spreadsheets, by working on code smells, refactoring, and testing for spreadsheets. But now it's time to turn the arrow, to look at source code from the perspective of spreadsheets. Because spreadsheets have some amazing properties that we as software engineering could learn from. They have directness, which means that you don't have to search for where your stuff is. You can just point it and it will be right there. And spreadsheets are live. You don't have to compile them. You just change something and immediately the value will change, like in a spreadsheet. It immediately updates without you doing anything. So that's it. Thanks for being on my talk. Spreadsheets are code. If you want to talk about this more, you can download all the tools from my website. I'm on Twitter, I'm on email, and also I will be here all week. So if you want to hang out to brainstorm about possible research collaborations, or if you want to do something together, you know where to find me. Or of course, you could ask a question now.
Questions? Max.
Thank you for your good talk. Oh.
It's for the internet.
Yeah. Thank you for the great talk. What else do you see is also code beyond a spreadsheet in terms of tools people use every day?
So what else do I think is code apart from spreadsheets? Well, obvious things, maybe like Microsoft Access is something that's, I think, a little bit out of many people's scope. It's not really a database, so there's not lots of database research into it. There's also a bit more powerful, so it's a bit too powerful maybe for the end user programming community. So that's something, if you would be interested in doing research into that, that could be a good candidate. It's a bit more powerful, but it's not as widely used as spreadsheet. I mean, in terms of the number of people that can do it, nothing compares to Excel.
Brian? Patience.
Hi, great talk.
Thanks.
So, how do you think spreadsheets differ from image-based programming languages like Smalltalk or Common Lisp? There's similarities, but I think you have some insight on how they're different.
Yeah, so one of the things that's obviously very different is it's a combination of data and program. So within a spreadsheet, you have the data always right there, and that's not always the case in something like Lisp. And also, especially Lisp, the syntax is not very forgiving.
Some of them.
I know some people like it, but that's a clear difference, I think, that the fact that spreadsheet formulas are relatively easy is probably something that also sets it apart. But I think the data aspect is way more important. It's really TBD, basically, for everyone. This is how people make spreadsheets. You put in data, you have some sort of idea of what you want, and you play with the formulas until it looks like what you want.
Back there? Then Mike.
I have a question because I agree with you that spreadsheets are widely used by many people, even in the bank, in many industries. My only concern about the spreadsheet is what you think about the language problem. Because, for example, in the case of Microsoft Excel, all the formulas are translated to the country that you set up the software. So I think it's a big problem because if I used to use the formula in my own language, then I switch to English and nothing matched. So have you targeted this kind of problem or have any idea?
Yeah, so we haven't really targeted because internally you can always ask Excel to give the formulas in English. So our parser, for example, only does English. But it's a serious problem. And I don't know if the problem is big enough not to warrant a solution. Maybe it is accessible to people because it's in their own language. We haven't especially researched that, but I can imagine that it has contributed to the widespread of spreadsheets because it's in people's own language. It could be easier that way, so I don't know. It's not just a problem, as you said, if you're transferring, it's also a huge problem with Googling, we know that. People want to Google for what they see, and then if it's Dutch, there are not so many of us, so it's a lot harder to find stuff than if you would Google the same English formula.
Mike?
So, speaking about the future, how about higher order spreadsheets?
Yeah, why not? Yeah, seriously, why couldn't that be a...
Sure, but are you doing that or not? Because, I mean, usually in practice you don't have one spreadsheet, you have many of those, and there are some complex relationship between them, and there is the entire ecosystem of how they are handled and so forth. So, is there anyone who's doing that, or are you? Is that your new paper? Or?
So it's not really something that I'm working on currently, but there's work by Simon Pete and Jones of Haskell about 10 years ago that proposed user-defined functions within using formulas. So you don't have to use VB to write user-defined functions. You can use formulas to write functions, and that is something in the direction of making spreadsheet more powerful. So there's certainly some work in that area, but I'm now, as I showed in my slides, a little bit more working on bringing the stuff to software engineering. And
yeah, he probably also expects fixed points and stuff.
Yeah, so if you do start higher order functions, obviously you open a can of worms of everything. How would the syntax look like? I mean, it's a very nice thought experiment, but I don't know if the trade-off of more power would be worth it because you'll add very complex features.
Okay, Evelina, so that was the programming language version of how do you make it bigger. Let me ask sort of the hacker's version of that. Do you have a theory of architecture or higher level views of how you ought to design sets of spreadsheets and how you could talk about good designs versus bad designs?
One of my grad students, that unfortunately is the one that's not here this week, is working on that. So he's working on a sort of a templating language where you can design your spreadsheet at a higher level. Is it time? Is this time? Something? So he's working on a templating language where you can define an architecture for your spreadsheet and it generates a spreadsheet that you can then fill out. And if you change your mind later, if you think, okay, this is not a good layout, you can go back to the template and rearrange your spreadsheet and it rearranges the data with you. So that's certainly something that we are working on.
Okay. Last question here. Yes?
Yes, so you have done some studies on usage level Excel, so how many Excel users and how many programmers with Excel sheets there are. Have you looked into how many of them actually do programming in Visual Basic?
No, we haven't done that. Also, the studies that I cited were not my studies. They were studies by other people. So we are investigating VBA a little bit, but so far everything we focused on was formula-based because, well, firstly, it was easier. It was lower hanging fruit, but also the people that program in VB, then you're really talking about programming. Those people know they're programming. They sometimes do use tools, and there are acceptable IDEs for VBA. So the problem there isn't as big as in spreadsheet. For instance, a person that, like I mentioned in a bank, mapping all the risk, but not realizing he's a programmer. So he's not going to reach out for tools or techniques or methods. So it was also more problematic within the formulas. That was my answer.
Cool. Last question.
Really last question.
So I know we only got a very small demo of the Excel-inspired programming language. Do you have could you share us your thoughts on how this compares to functional reactive programming, where you also have variables that are updated, and as soon as a variable is updated, all of the functions it is used in are recomputed?
Yeah, so the biggest difference between the demo I showed, which is also, I will tweet the link later, it is on my website, so you can play with it if you want to. The biggest difference is that you're looking at data at the same time. So you have one view of your it's Brad Victor with a spreadsheet. You have your program and an instantiation of that program, and of course, a tree is very nice, but not very realistic, and we think a grid representation, and maybe this will eventually also include arrays or nested arrays, more complex structures, that is really helping you program. It's a very realistic scenario where you look at data and you think, oh, I need the minimum or something more complex.
That's Evelina again.